So how do we actually compute the probability that Sally has cancer given that she got a positive result on the test? So let's go back over to our Excel sheet here, and I'm going to try to make this a little bit interactive. So, whoops. So let's just clear this out, and let's just pretend that there's 1,000 people in our population. We know that 5% of those people have cancer, right? So let's start, we'll just call this population. And so just to make this interactive, I'm going to take this 1,000, I'm going to multiply that by this number here. So that means that should give us 50 people have cancer, which is going to leave 950 who don't have cancer. So that's just going to end up equaling this minus this. Okay, now let's see, I want to actually scoot these over. So that's going to mess up my numbers, isn't it? No, it didn't. Okay, cool. So now that we have these 50 people there, we know that there is this sort of true positive rate. So we know that 95% of these people are going to be correctly classified as having cancer. So we're going to end up with a fraction here. So let's take this, and we're going to multiply this number by this probability. And so we know 47.5 people end up getting a positive result on the test when they have cancer. Just so we don't get these fractions, I'm going to increase our population to 10,000. Alright, so now we got 475 there. Sounds a little bit more. You can't have half of a person, even though the math will still work out just fine. So then we also know that it's going to be this minus this people are going to be classified as negative whenever they get the test. So these are the people with cancer, these 500, and these 9,500 are the people without cancer. And 475 people from this population of people who do have cancer get correctly classified. So that'll be like a true positive. And this is our false negative. Okay? And so of the 9,500 people who don't have cancer, we know that this number, the 9,500, times the probability of getting a positive result given not having cancer, this number, is going to be people who took this test who didn't have cancer, but it still told them that they had cancer. So that would be a false positive in this context. And then that's going to leave 9,500 minus 950 people who got correctly classified as not having cancer. So now we can think about these four numbers here. We got our true positive, our false negative, our false positive, and our true negative. So when Sally walks in and gets her test and it says that it's positive, what's the probability that she has cancer? In other words, what's the value of this conditional probability? What's the probability that Sally has cancer given that she got a positive result on the test? So it's a simple computation here. We just take an equal sign to compute this, right? And we want to put the true positive rate over the entire population of people who got a positive result on the test. So there's all these people who got a positive result, and only a fraction of those people had only a fraction of those people actually had cancer. So what's that value? It's only 1/3. So that is the counterintuitive nature of this. Even though you've got sort of this 95% true positive rate and then only a 10% false positive rate, which seems pretty accurate, if someone comes in off the street, takes the test, and they don't have cancer, there's still it's still a pretty low probability that they actually have cancer, given that they got a positive result on the test. Now the interesting thing about this is, I'm just going to put this in. I'm just going to put this in this color here so you can see that. The counterintuitive part about this is that, well, one, I'm wondering, was this counterintuitive for you as you watched the video? It was for me when I first learned about this type of thing. But people don't take these base rates into account. So if I put 0.01 here, that changes that number. So when you have something that's really rare, even if you have a sensitive test, the probability is going to be pretty low, this conditional probability, even if they have that positive result on the test. So priors, as you raise this up, so let's say it's 0.50, that's almost like the assumption a lot of times. It's like, oh, it's half and half, and you're categorizing things. When we do naive Bayes, and when you do actually lots of classification types of problems using other techniques, a lot of times you're assuming that that base rate in the population is 50-50 when it's really not. But it's still for some reason the algorithms still seem to work fairly well, and it's usually not something critical like detecting whether somebody has cancer. So I just want you to know that taking this base rate or this prior probability into account is really important, because it can lead to drastically different probabilities, drastically different values on this probability of A given B, sort of at the end of the day. But also know these vocabulary terms: prior probability, probability, and conditional probability. And we'll use these concepts whenever we're running through the naive Bayes example, and also whenever we're validating the model. All right, I'll see you in the next video.